This is question 9, part B of the 2018 higher level mock exam. It's a topic 6 and 10 question that asks about gravitational potential, where we are given the graph that relates gravitational potential and distance from the center of a planet, and we are told the radius of the planet is 2.5 times 10 to the 6 meters. The first question asks us to use data from the graph to find the value of g naught, which is the surface acceleration or the gravitational field strength at the surface. The mark scheme uses this straightforward formula that relates the potential to the distance from the center. And so what needs to be done is the potential needs to be found for that location. So at the surface of the planet, where the radius is 2.5 times 10 to the 6 meters, we go to the curve, and we find that it's minus 9.8 times 10 to the 6 joules per kilogram. Divide that by the radius, and that gives us the surface acceleration of 3.9 meters per second squared. There's two other ways of solving this problem. One is by using the gradient of the tangent of the curve at that point, and there's been examples in the past where this has been the method that they have insisted on in the mark scheme, so it is good to know it. This makes use of the fact that the gravitational field strength is equal to the rate of change of potential with distance. And so this is the gradient of the tangent of the graph. So drawing a tangent on allows me to calculate an acceleration due to gravity value. Mine ends up a little bit different from the other method due to the different interpretations that can be made of drawing the gradient. The third way of solving this question is to use the equation that was derived in part A of this question, and realizing that this holds true along this curve for any given radius and potential. So all you need to do is find a point on the graph. Here I've chosen one where it is easy to read the points off of the graph, where this is 6 and this is minus 4, and I have substituted those two values into the equation after having rearranged it to solve for g naught. Again, that gives me an answer of 3.8 meters per second squared, which is very similar to the answer in the mark scheme. Part 2 of this question asks about the energy required to raise a satellite up to a given height above the surface of the planet. Because the gravitational field strength is changing from the surface up to the location where it is being launched, we cannot use the MGH equation, and we have to use the change of potential equation instead. One of the other difficult aspects of this question is that this distance is the height above the surface, and so it's essential when using the graph to realize that we need the distance from the center of the planet before we can find the potential. So here we're using the change in energy as the mass times the final potential, subtract the initial potential. The final potential then will be the potential at a distance of 5.5 times 10 to the 6 meters from the center of the planet. So going to the graph and looking at 5.5, we can get a value of minus 4.2 times 10 to the 6 for that location, and then at the surface of the planet we have this value that we already used here. When we do this subtraction, the double negative ends up becoming a positive and gives us an overall positive value for the change in energy, which is what we are expecting because there is a net gain of gravitational potential energy in this situation.